Everything looked normal. The model passed validation. The test scores were clean. The deployment review was approved. But buried deep inside the training data was something the security team never saw. Not malware, not a stolen password, not a prompt injection attack. Something quieter. The AI had been poisoned before it ever went live. Welcome to Security of AI. Today's case is about one of the most dangerous and least visible threats in artificial intelligence: data poisoning. This is not an attack on the user interface. It is not an attack on the firewall. It is an attack on the foundation of the model itself. Because before an AI system can make decisions, generate answers, recommend actions, or classify threats, it has to learn. And what it learns from matters. If the data is corrupted, manipulated, biased, or deliberately sabotaged, the model may learn the wrong lesson. And the worst part is this: a poisoned AI system can still look trustworthy until the hidden trigger appears. Modern AI systems are trained on enormous amounts of data. Web pages, code repositories, images, sensor feeds, documents, user behavior, open-source datasets, third-party data, crowdsourced labels, and sometimes data from sources nobody fully controls. That scale creates opportunity. An attacker does not always need to break into the model. Sometimes they only need to corrupt what the model learns from. A few poisoned examples, a few misleading labels, a few planted documents, a few insecure code samples, a few manipulated sensor records. The data enters the pipeline. The model trains on it. The behavior becomes embedded. And by the time anyone notices, the poison may already be inside the model's weights. This is what makes data poisoning so dangerous. The model may not fail all the time. In fact, it may work perfectly under normal conditions. It may answer questions correctly. It may classify images accurately. It may recommend the right actions. It may pass routine testing, but under the right conditions, it behaves exactly the way the attacker intended. That is called a backdoor. The AI behaves normally until it sees a hidden trigger, a pattern, a phrase, a pixel arrangement, a file name, a sensor condition, a specific code comment. Then suddenly, the model changes behavior. The system that looked safe becomes unreliable at the worst possible moment. There are several ways this attack can happen. First, availability poisoning. This is when attackers add junk, misleading, or corrupted data to degrade the model's overall performance. The model becomes less accurate, less stable, and less reliable. Second, backdoor poisoning. This is more subtle. The model behaves normally most of the time, but when it sees a specific trigger, it produces the attacker's desired output. Third, concept corruption. This is when attackers slowly shift what the model believes something means. A model trained to detect fraud may become blind to a new fraud pattern. A model trained to identify threats may learn to ignore certain indicators. A model trained to generate secure code may start recommending insecure design patterns. The danger is not just that the AI makes mistakes. The danger is that the mistakes may be planted. This is why data poisoning is not only a machine learning problem, it is an AI supply chain problem. Think about a coding assistant trained on public repositories and technical forums. If attackers plant insecure code examples, misleading documentation, or vulnerable configuration patterns into sources likely to be scraped, the AI may later reproduce those patterns. A developer asks for secure authentication code. The assistant produces something that looks professional. It compiles. It appears reasonable. But the pattern is weak. The vulnerability was not typed by the developer. It was learned by the model. That is the nightmare scenario. A compromised AI system may distribute bad decisions at machine speed across thousands of users while appearing helpful the entire time. Traditional cybersecurity asks familiar questions. Who logged in? What system did they access? What file did they change? What did the logs show? But data poisoning asks a harder question. What if the system was trained to be wrong before anyone started watching? There may be no obvious breach, no ransomware note, no suspicious login, no malware alert, just a model that learned from corrupted data and now behaves in ways the organization cannot fully explain. That is why AI security cannot begin at deployment. It has to begin at data collection, at labeling, at curation, at training, at validation, at monitoring, and at independent assurance. To defend against poisoned AI, organizations need more than accuracy scores. They need data provenance. Where did the data come from? Who touched it? Was it changed? Was it verified? They need dataset configuration control. They need anomaly detection. They need adversarial testing. They need independent validation sets. They need behavioral regression testing. They need red team testing designed specifically for AI systems. And most importantly, they need evidence. Evidence that the training pipeline was controlled. Evidence that the dataset was reviewed. Evidence that the model was tested against poisoning risks. Evidence that the AI system can be trusted. This is the security of AI mission. Govern the system, defend the pipeline, prove the result. The frightening part is not that AI can be poisoned. The frightening part is that poisoned AI may still look normal. It may pass tests. It may satisfy users. It may improve productivity. It may even appear trustworthy until the hidden trigger appears. And by then, the organization may not be dealing with a software bug. It may be dealing with a compromised decision system. That is why data integrity is not optional. It is the foundation of trustworthy AI. And if we cannot prove what the model learned from, we cannot fully trust what the model does next. I'm Bobby, and this is Security of AI. Thanks for watching. Please like, subscribe, and comment below.